welcome back. And this is lecture 2. So when we ended the last lecture, we were talking about how to handle quantities which have wide variation of their values, right? So as it turns out, in an RF system, the signal power that a receiver receives can vary from all the way from a few picowatts to the transmitter sending out all the way to few watts, right? So when you're talking about power levels of that range, which vary from 10^0 to 10^-12, then obviously you see it becomes sometimes clunky and inconvenient to use the linear scale, right? So mathematicians and scientists over the years have figured out a more convenient way of dealing with these numbers when they tend to vary by these huge proportions, and the methodology of choice is to use log scale, and that is exactly what we are going to do in this course. We are going to use log scale, and whenever you read any RF textbook or RF paper, you are going to see terminologies which refer to signal powers in dBm, dBW, or voltages as dBV, and so on. So the first part of today's lecture is to get us reacquainted with these terminologies. I'm sure all of you know what a dB scale is, but just to touch base, we'll ensure that we are all in the same page with respect to these terminologies. Okay. So let's get started. So the first thing that we should always understand is dB is a ratio, and which means this is unitless, right? So there's no point in saying that I have my voltage is 0 dB or my power is 0 dB. That doesn't convey anything. So that is why whenever you want to convey an actual quantity which has a unit, you cannot really say that you cannot really convey it in the form of dB. You have to convey in the form of dB and then also quantify with respect to what unit you are taking that ratio, right? So what I mean by that is, let's say I am trying to deliver 1 watt of power, right? So let's say power is 1 watt, and I take a dB of it. And what do you mean by take a dB of it? The decibel system is essentially 10 log to the base 10 of whatever quantity we are trying to convert to log scale, right? So I can simply write 1 watt, but this doesn't make any sense because I cannot take a log of 1 watt, because I can take a log of, in principle, I can take a log of a unitless number, but this is not a unitless number. So what we tend to do is to say that we have to make this number unitless, which means that what I'll do, I will normalize everything with respect to 1 watt, right? Or in other words, if I say that I have a P in watt, I would like to quantify this quantity in watt in dB scale. So what I'll do is I will take 10 log of to the base 10 of P in, right, in expressed in watt. So P in watt, and I will normalize it with 1 watt, right? Which essentially means that the unit part is irrelevant. The ratio still stands, but now I can take a log of the argument, and in order to convey that I have taken this ratio of P in, I have divided P in with respect to 1 watt. We call this dBW, right? Where W essentially means watt, and if I say that I have let's say a 0 dBW power, what would 0 dBW power signify? 0 dBW power will signify that the argument is 1, which means that P in will be 1 watt, right? So P in will be 1 watt, right? So if I say that I have a unit, I have 10 dBW, what does P in mean? 10 dBW means P in is equal to clearly 10 watt. Similarly, if I say my unit is 20 dBW, what is P in? Clearly P in is 100 watt and so on, right? So what is the easy hack to remember is that if I go 10 dB, if I increase my power strength by 10 dB, right, I go by, so essentially if I go by 10 here, if I add 10 in dB scale, I multiply 10 in linear scale, right? Again, I add 10 in dB scale, so I multiply 10 in linear scale, right? So similarly, if I say my P in is again 1 watt means 0 dBW. So in linear scale, this is in decibel. So if I say I have 2 watt, right? What does it mean in decibel scale? So clearly 2 watt means 10 log of 2, right, which is approximately equal to 3 dB. In this case, in decibel level, the P in will be 3 dBW, right? Similarly, if I double further, I go to 4 watt. So in decibel scale, this will be again addition of 3, which means 6 dBW. And then I go to 8 watt, this will be 9 dBW, right, and so on. So what does it mean? What is the hack? The hack is if I go multiply by 2 in linear scale, I add 3 in dB scale, right? So this is all you kind of need to know to get a ballpark estimate of where we are, right? Suddenly if I tell you that I have a 30 dBW power, right, and I want to reduce the power from 30 dBW to 20 dBW, okay, so then how much am I decreasing? I am essentially decreasing the power by 10x, okay. So the another thing that you should keep in mind is, if I say that, let's say I have a powers, let's say I have an antenna or I have a transmitter that is sending out, I don't know, 10, let's say 0 dBW power. Transmitter 1 is sending out 0 dBW power. Transmitter 2 is sending out 30 dBW power, right? Quite high numbers. Or let's say I say that this guy TX1 is sending out 10 dBW power and TX2 is sending out 30 dBW power, right? So can you tell me what is approximately TX1 plus TX2 sending out? Approximately, I do not want exact. Is it sending out 40 dBW? Clearly no, because 40 dBW means 10x over 30 dBW, right? But in this case, my 10 dBW is anyhow in linear scale. TX1 is sending out 100x lower power than TX2. So if I combine both their powers, if one is 100 times lower than the other, adding those two powers barely changes the total power of TX2, right? So TX1 plus TX2 sends out also approximately 30 dBW power. So essentially, when you in log scale, when you are trying to add two linear quantities which are widely varying, right, which have significant differences in linear scale, and you are trying to add them up in log scale, you essentially choose the higher one. Okay. So again, the other part that I did not go to. So let's say I am sending out minus 10 dBW power, right? So what does minus 10 dBW mean in linear scale, right? So again, from 0 I have come down by 10x, by 10 dBW, which means from 1 watt I will go down by 10x, right? So here I am going to divide by 10, which means I have 0.1 watt, right? So I'm going to have 0.1 watt. Okay. Similarly, if I say that in decibel level I am sending out minus 6 dBW power. What does it mean? You see that from 0 dBW I have come down by 6 dB, which means I have to divide by 2 twice, right? So which essentially means that here I have to divide by 4, which means I am sending out 0.25 watt of power, right? It's quite simple once you get accustomed to it. Now once you know this, you will be able to you should be immediately able to understand what the other units mean. Let's say suddenly you find out that somebody is using an unit of dBm. Can you guess what would dBm mean? And I'm sure your guess is right. So if dBW means power normalized to 1 watt, dBm should mean power normalized to 1 milliwatt, right? So this is basically 10 log to the base 10 P normalized to 1 milliwatt. P obviously expressed in watt, normalized to 1 milliwatt, which essentially means that again 0 dBm should mean, so this is a dBm, and this is, let's say, P in linear scale. So 0 dBm should mean 1 milliwatt. Similarly, minus 10 dBm should mean 10x lower than 1 milliwatt, which means 100 microwatt or 0.1 milliwatt, and so on. And then what is the relationship between dBm and dBW? So clearly, so 1 dBW should mean 30 dBm, because essentially you have 1000 milliwatt by 1 milliwatt, right? And 10 log of that is essentially 30, right? Okay. So similarly, once we have this, we do not stop there. So there are other ways of expressing units also. So when you have a dB scale, why stop at watt? We can also use volts, or even you can use amperes, right? So there are units of dBV, but now you have to be slightly careful, because initially the log scale was used to express to express watts, powers in log scale, right? Hence whatever was 10 log, a 10 log of power essentially means something 20 log of voltage, right? Because essentially the conversion from power to voltage goes as V squared, right? If something is if you have if you have a resistor of certain value, and you know that the power across it is some watt, the voltage across it will be whatever that is under root that watt, and then some scaling factor. Or in other words, if you know that if you have V voltage across a resistor in power, you have to square it and then take 10 log, right? So squaring and then taking 10 log is equivalent to saying I will do 20 log of the voltage value without squaring, right? So that is why when people express units in dBV, we tend to use again dB, but with a slight modification. dBV is essentially 20 log. So you have to be careful of this. This is 20 log 10 of whatever voltage expressed in volt divided by 1 volt. Okay, so essentially again the same thing. If I have 0 dBV would mean 1 volt. Similarly, can you guess what minus 20 dBV will mean? So here minus 20 means in voltage scale you are going by minus 20, which means in linear scale you are going by divide by 10, because note that in case of dBV this is 20, not 10, right? So here you divide by 10, right? So here you have gone by 20, so here you go by 10, so which means this is 0.1 volt. Similarly, if you go to plus 1020 dBV, right? So with respect to this you have gone plus 20, so with respect to this you are going to get multiplied by 10, that is 10 volt, and so on. Similarly, if you double, what happens if you double? So let's say I double, I go 2 volt. 2 volt means now it becomes 20 log 2. 10 log 2 is approximately 3, so 20 log 2 is essentially 6. So doubling of the voltage in dBV essentially means you add up 6. Okay, fine. So as long as we understand this, there should not be any problem, right? Okay. Refresher 2 is that of Fourier analysis, right? So we have, I'm sure all of you have done Fourier analysis in your undergrad courses. So what does it essentially tell you? It basically tells you that if you have a periodic signal, so say Vt is periodic with time t, that is, I can express Vt as V of t plus capital T, right? So an example, I mean, you can always draw something which is periodic. So let's say you have a Vt which is something like this. This is, and then this, the same thing repeats, right? So let's say this is again this, and this again goes like this. Here also you see something like this, and so on, right? So this I mean, it's a very poor drawing, but you get the idea. You get the idea that you have this unit here. You have this unit here which keeps on repeating, right? So if I say that this is or it's not only that unit, I can basically say that I can start from, let's say, here and maybe end somewhere over here, and that unit also repeats, right? I can start here and maybe end somewhere over here, and that also repeats, right? Similarly, I can start here and end here, that also repeats. Basically the same unit repeats, and each of these durations are t, right? So by definition, right? So this is t. So if this condition is satisfied, then we know that Vt can be expressed as a sum of complex exponentials that is Cn e power j 2 pi by t, that is a repetition interval, times n times t, and n is minus infinity to infinity, right? And where Cn, so let me write it again. So dt can be expressed as summation of some complex number Cn, or summation of some complex number Cn weight times e to the power j 2 pi by t times n times t, where n goes from minus infinity to infinity, where Cn is equal to 1 over t, where t is the time period, integral minus infinity to infinity v of t, sorry, I made a mistake here, integral of v of t times e power minus j 2 pi by t n t dt, and this integration limit is for one period 0 to t. Now you can choose this period to be t1 to t1 plus t, or any period, but it has to be within one period, right? So what is this basically telling us? It is basically telling us that if you have any signal which is periodic, which repeats with time, which repeats with some intervals of time, I can basically break it down into summations of complex exponentials, right? So this basically means that v of t, you can say when Cn equal to 0, let's say, is this becomes C0 e power j, if Cn equal to 0, then it becomes C0. If Cn equal to 1, this becomes C1 e power j 2 pi by dt. If Cn equal to 2, this becomes C2 e to the power j 2 pi by t times 2t, and so on. Similarly, for n is negative, this will become C minus 1 e power minus j 2 pi by dt, and so on, right? So now why is this representation important? This representation is important because it helps us to understand what is the strength of a signal. Now let me elaborate on that. So let's say I tell you that we have a signal, we have a sinusoid. So now the question is, why do we care about doing Fourier analysis, especially when we're dealing with RF signals, right? So why Fourier? The reason is, how do we know if a signal is weaker or stronger than another signal, right? So how do we know? I mean, I say that I have a sinusoid. Let's say I have a sinusoid of 1 volt amplitude. Like, very poor drawing, slightly better maybe. So let's say it has 1 volt amplitude, 2 volt peak to peak, and I have another sinusoid of, let's say, 2 volt amplitude, right? Same or different frequency, doesn't matter. How do I know which signal is stronger? Clearly the signal with 2 volt amplitude is stronger than the 1 volt amplitude. And how do we know? Note that it's not necessary. The signal with 2 volt amplitude always has a higher voltage as compared to the 1 volt amplitude, right? I can always move the signals in such a way that where the peak of one signal crosses the zero of the other signal, and so on, and I can sometimes one of the signals is stronger than the other, right? But how do we know that one signal has How do we know one signal is stronger than the other? We know that because the power content of one signal is higher than the other. What do I mean by power content? So let's say this is assume that this is a voltage across a resistor, right? If this is a voltage across a resistor of value R, what is the power dissipated, right? So if this is a voltage across a resistor R, then P voltage power dissipated across a resistor R will be, so the amplitude square, right? V amplitude square divided by 2R, right? So clearly the amplitude has the information of which is a stronger signal. Now this is quite trivial, but then if I tell you that your signal is not a pure sinusoid, right? Maybe your signal is periodic, but maybe a summation of sinusoids, right? I add these two sinusoids up, maybe the sinusoids, when they add up, they become, I don't know, maybe sometimes this is like this, sometimes this, and so on, right? And it keeps on repeating. Then how do I know what is the power content of this signal, right? I don't know. I cannot really make a comment on what is the power content, because this is not a sinusoidal signal. Note that this is true only if this expression is true only if your signal is sinusoidal, which means that in order to come to the power content, or in order to understand whether a signal has a higher amplitude or a lower amplitude with respect to another signal, let's say I have another signal which goes something like this, and so on. How do I know the signal on the top has a higher power than the signal on the bottom, right? So I don't know, right? So even if I tell you the amplitudes of this, just looking at it, it's probably not very easy to guess. So one of the motivations of doing Fourier transform, one of the motivations of doing Fourier analysis is to basically deconstruct these signals into sum of sinusoids or sum of complex exponentials, and then if I can then say that any of these signals is a sum of so many sinusoids, and each of the sinusoids have so much amount of power, then I can probably add up those powers and say that, okay, this signal has so much power and that signal has so much power, right? So it's basically a easy hack to analyze signals, right? So that is one of the reasons we would like to break our signals down to sinusoids, right? So now if I go back one page, you should instantly recognize that many of you probably would be more familiar with the other form of this equation. So this, if I write it as C0 plus, let's say, summation of n equal to as infinity to infinity Cn e to the power j 2 pi by t and t, or simply I write for all positive n equal to 1 to infinity plus c negative n c minus n e power j 2 pi by t sin t. Now depending upon whether Cn can be broken down into, if it's a complex number, Cn can be broken down into a plus jb, right? Cn can be, say that is an plus jbn, right? So similarly, c minus n can basically be reduced to an minus jbn. Then some of you might be familiar with the other form of this expression, where I do not write anything in terms of complex exponentials, but I use the fact that e power j 2 pi by t n t plus e to the power minus j 2 pi by t n t this is equal to twice cosine pi by tnt, and similarly j 2 pi by tnt minus this becomes twice j sine of 2 pi by tnt, right? So regardless of whichever you are familiar with, it doesn't matter. The motivation remains the same, that there is a significant need for our ability to deconstruct a signal, a periodic signal, into sum of exponentials, sum of complex exponentials, because it would help us. It would help us not only to extract the power of each signal, but also it will also help us to understand what is the frequency component of each signal. If you remember, we talked about in the first lecture, there is significant need of filtering in RF analysis and RF design. So when we say filtering, we essentially mean that we would like to pass certain signals of certain frequency and not pass signals of other frequency. So in order to understand which frequencies to filter out, we need to first understand what frequency components exist. And if we know what frequency components exist, then we need to also know how to do Fourier analysis, right? So that's essentially one of the motivations of why we need to do Fourier analysis. So given that the motivation is clear, right? So a quick recap of couple of Fourier series. So let's say our signal is e power j omega naught t, right? So let's say Vt is e power j omega naught t, right? So what is the Fourier components, right? So firstly, is it periodic? How to check? So obviously it is periodic, because if omega naught t, so let's say I can always add, say this is equal to e to the power j omega naught t plus 2 pi. I can always add 2 pi, which means that this is e to the power j omega naught t plus 2 pi by omega naught, which means a t exists. So the t exists which is equal to 2 pi by omega naught, where the signal repeats itself, which means it is periodic. So now what is the periodicity? Periodicity is t, which is 2 pi over omega naught. So what is our C1 is equal to 1, right? So why? So let me break it down again. So we are basically saying Vt is equal to summation of Cn e to the power j 2 pi over t, that is the periodicity, times nt, right? So clearly C1 is equal to 1, because C1 gives, if n equal to 1, I get C1 e power j 2 pi over t, capital T times t, which is equal to this. So this satisfies, and clearly when what happens to C0, right? So C0 is 0, because no such term exists in complex exponentials. Similarly, Cn, all other Cn, when n is not equal to 1, are 0, right? So what does this essentially, again, what does this mean? This essentially means that this a complex exponential, right? A complex exponential has only one frequency component, right? So how do I express this in frequency domain, right? So in frequency domain, when I say I want to express this in frequency domain, what do I mean? I essentially say that I have f here, and I am plotting the strength of the signal, right? I am not plotting with respect to time, or here when I say strength, in this case I am saying the amplitude. of complex exponential, right? So if I do it with respect to omega instead of f, right, and f and omega are essentially a scaling factor. If I do it with respect to omega, what do I see? At omega equal to 0, right, what do I have? At omega equal to 0, omega equal to 0 means which component that I am looking at? I am looking at C naught, right? So C naught is equal to 0, so I get 0. At omega equal to omega naught, what do I get? I get 1, right? So omega equal to omega naught, I get 1, right? And note that in this case, when you are plotting this with respect to omega, this is represented as a delta function, right? Because the strength of the signal is basically the integral of. So how do we express this in frequency domain? Often you will hear in RF circuits that we refer to a signal having a tone, right? So this is often referred to as Vt equal to e to the power j omega naught t. If this is expressed in volts, let's say it's volts, as a tone of 1 volt at omega naught, at frequency omega naught radian per second, or omega naught by 2 pi hertz, right? So in the book, when somebody tells you a signal has a tone, all it means is that in time domain you can express that signal in the form of e to the power j omega naught t, right? So if I tell you that a signal has a tone at let's say I tell you that Pt has a tone at 1 gigahertz, then what will be Vt? Vt will essentially become a tone. This is not sufficient, this information is not sufficient. I should also tell you what is the strength of the tone. Let's say I tell you that Vt has a tone at 1 gigahertz of 2 volts, which means that Vt is essentially 2 volt e to the power j 2 pi 1 gig, that is 10 to the power 9 times t, right? That's what it means, right? That's all it means. However, at this moment of time, you turn around and say that there are no complex exponentials in real signals, which will be correct. Instead of getting e to the power j 2 pi, we get cosine and sine. But what is a good thing? We know that a cosine omega naught t can also be expressed as e to the power j omega naught t plus e power minus j omega naught t divided by 2. Similarly, a sine omega naught t can be expressed as e to the power j omega naught t minus e power minus j omega naught t divided by 2, which means that this signal has tones of 1 over 2 at omega naught and minus omega naught, and this signal has tones of 1 over 2j at omega naught and minus 1 over 2j at minus omega naught, right? If I have to express that in graphical format in frequency domain, I'm sure you have seen this also in your UG courses. With respect to omega, if I now note that I'm plotting this with respect to omega, not with respect to time. I'm not plotting cosine with respect to time, I'm plotting with respect to omega, which means that here I am plotting the strength of the signal, right? Here I am plotting the strength of V of omega, right? I'm not plotting V of t. This is strength. Basically, you can think of it like I'm plotting the amplitude of the sinusoid, right? I'm trying to capture the amplitude of the sinusoid, not plotting, I'm trying to capture the amplitude. So then I know that this is only a single tone signal, and the tone is at omega naught, plus omega naught, and minus omega naught, right? Your cosine omega naught will be expressed as 2 delta Dirac functions having an area, right? The area of the delta Dirac function will be equal to half, right? So I'll basically mark it as 1 over 2, and the phase is what? This is only the magnitude. The phase information is, the angle information is 0, because Cn is basically half is real half, right? It doesn't have any imaginary part, right? So this is for V of omega to be is equal to cosine omega naught t. If we have sine omega naught t, the amplitude information, the magnitude information does not change. You still have tones at omega naught and minus omega naught of strengths half or 1 by 2, but you are going to have phase information of 90 degree plus and minus 90 degree, right? Okay. So this is as far as dealing with sinusoids are concerned, but I mean, rarely you also find pure sinusoids, right? But you find periodic waveforms which are non-sinusoidal, right? So that's what Fourier series gives us. One of the other common sinusoids that you are going to encounter in this course is one of the most common periodic signals that you are going to encounter in this course is a square wave. So let's also briefly recap what are the frequency components of a square wave. We'll take the example of a square wave which is symmetric and has a 50% duty cycle, right? So let's say I have a square wave, I have V of t is a square wave. So let's say V of t is a square wave. It goes from 0 to 1, and this goes like this, so on. Right? So this is t and this is t by 2. Okay. So I'm interested in finding out what is the frequency component of this square wave, right? So easy, right? So I know that this V of t is again summation of Cn e power j 2 pi by t, because t is the periodicity here, right? Nt over n, summation of over all n. Then Cn is essentially 1 over t integral of, this is V of t times e power minus j 2 pi over t and t dt, and I can choose any one time period. Let me choose 0 to t, right? So essentially Cn becomes between 0 and t by 2, your Cn is 1 and the rest is 0, so I can basically have the integral between 0 to t by 2. This becomes e to the power minus j 2 pi over t and t. Then this becomes 1 over t. This is 1 over minus j 2 pi over t and t by negative j pi over t n, and this is between 0 to t by 2. So what do I get? So I basically get, so this t cancels. I get 1 over minus j 2 pi n, and this becomes e power minus j 2 pi by t n times t by 2 minus 1, right? Which essentially means uh, Cn. So let's go back one page. Okay, let me write it down. So this becomes 1 by j 2 pi n 1 minus e to the power minus j, this goes, this goes, pi n minus j pi n, which essentially means if I take it to the minus j n pi by 2 common from, take it out from within the parenthesis, I get it to the minus j n pi by 2 by j 2 pi n, then I get this becomes power minus it for minus j n pi by 2. This is essentially 2j times sine of whatever is follows. So this becomes e to the power minus j n pi by 2 by j times 2 pi times n. This becomes 2j sine n pi over 2. So this j cancels, this j and 2 cancels. So we essentially get e to the power minus j n pi by 2 times sine n pi by 2 by n pi, right? So what is it telling us? It's basically telling us that C1 is equal to what? C1 is equal to 1 over pi. C2 is equal to basically sine pi by over 2 pi, which is 0, right? Or I should be careful, I should say mod of C1 because I am ignoring the e to the power minus j n pi by 2 terms. So let's concentrate on the mod. So then C2 is equal to 0. Similarly, mod of C3 is equal to again 1 by 3 pi. And similarly, mod of C minus 3 is also 1 over 3 pi. C minus 1 is equal to 1 over pi. What about C0? What about C0? C0 will be, so I can if you think about it, I can express this as divided by 2 times 1 by 2, right? So so sine n pi by 2 by n pi by 2 is effectively sine x by x when x tends to 0 is equal to 1. So C0 is basically half, right? And why does C0 equal to half make sense? What is C0 essentially? C0 is essentially, if I go back to our expressions, so what is C0? C0 in this case is nothing but, where did I write the other expression, right? So what is C0? C0 is nothing but 1 over t 0 to t pt dt. So basically this is nothing but the average, right? This is average over one period. So I do not even have to do the integral, right? If I know the average. So what is the average of a what is the average of this waveform over one period? This is half. So it's not a surprise that we are getting C0 to be half. But the key thing to note is that we are getting tones. We are getting tones at the odd harmonics of, or rather, we are getting tones at C1, C3, C5, and so on. We are not getting tones at C2, C4, and so on, right? So in other words, if I if I sketch the square wave, if I sketch the spectrum of the square wave or the frequency component of the square wave, right, again mod of v of omega, right, with respect to omega, I am getting C0, the location of C0 is omega equal to 0, so I am getting 1 over 2. Then at omega equal to C1 means omega naught, right, so which means 2 pi over t, 2 pi over t, I am getting 1 over pi, right, 1 over 3.14, so basically 1 over pi. Then at 2 omega naught, that is at 4 pi over t, we are not getting anything, we are getting 0. Then at 3 omega naught, that is 6 pi over t, right, we are getting 1 over 3 pi. Similarly, on the left hand side also, if since I'm sketching the modulus, I'll get at minus 2 pi over t. Then here I'm going to get 0. Then I'm going to get minus 6 pi over t, and so on. Right. So the key thing to note is that for a symmetric duty cycled 50% duty cycled, I should not say symmetric, I should say for a 50% duty cycled square wave clock, right, you get only odd harmonics of the fundamental frequency. Now, what is the fundamental frequency? I think I missed the definition of this. So 1 over t is often referred to as the fundamental frequency, or the fundamental tone, right? And multiples of 1 over t are referred to as harmonics. So multiples of are called harmonics, right? So essentially the harmonics of all harmonics of all harmonics of the square wave do not exist, right? If it's 50% duty cycle, you only get odd harmonics and you do not get even harmonics. And the other key result is that the strength of the odd harmonics are 1 over pi, 1 over 3 pi, 1 over 5 pi, and so on. What happens if, now I'm not going to prove this to you, you can do it yourself. What happens if the square wave is shifted to the left or to the right? Will the strength of the tones change? Obviously it will not change. I mean, you can think of it in terms of sinusoids also. If I shift the sinusoid to the left or the right, will the strength of the tone change? What does the tone mean? Tone is essentially a reflection of the amplitude of the sinusoid, right? So since the amplitude of the sinusoid is changing, the strength of the tone will not change, but what is going to change? The phase is going to change, right? So where is the phase information here? The phase information is embedded here, right? So this is the phase information, right? So at C0, obviously there is no phase, n equal to 0. At omega naught, when n is equal to 1, you see the phase is basically minus pi over 2, right? And similarly, the phase at omega equal to 3, you see the phase is at n equal to 3, the phase is 3 pi over 2, and so on, right? If I shift the entire signal to the right or to the left, right, so you are going to just add up the extra phases, and that will the only thing that is going to get impacted here is in the phase, not in the amplitude, right? Okay, fine. So we'll stop here for today's lecture. So this, we basically went back. This lecture and part of the next lecture will also still go back and refresh some of our old UG concepts, which we will take for granted later on in the course. So hopefully, I mean, if you are already familiar with this, bear with me for one more lecture, and then we'll start getting into a bit more of analysis and bit more of conceptual things with respect to RF analysis, right? Okay, I'll stop here. See you in the next class.